Alright, this is going to be a little display thing of a bunch of stuff that I've made using Desmos. It's like going to be kind of art. I mean, it's going to get better than this. This was something I made like a couple years ago when I was in high school. And it's just, I made a goblin looking thing using a bunch of different types of equations, like functions basically, that were restricted. And I just restricted them by looking at I think I just looked at the points. It tells you the numbers, and I just put it in. So it's pretty approximate. As you can see, he has a little beard made out of, I think those are tans or something. And then tan plus a parabola, and I have a sine wave plus a parabola, stuff like that. This one's okay. I'll show you a better one, though. I should probably get to these quicker, because there's a bunch of cool ones. Here's something I made. It shows you how you can find a point, a circle that can go through 3 points, any 3 points, and you can find a circle that goes through them. How do you do it? Well, you're trying to find, if you find a point in the middle that's the same distance from all 3 of them, then that would be the center of your circle, and that's where these 2 lines meet. Now, why do these 2 lines always meet at the center of a circle like this? Well, it's because basically you have these 2 lines here that you can't see. I think I can actually make them visible. Or are they? No, you can't. Okay. So there's these 2 midpoints. This is the midpoint between these 2 points, and this is the midpoint between these 2 points. And everything along this whole line is a midpoint between this, is equidistant from this point and this point, and everything along this whole orange line is equidistant from this point and this point. So technically, if you look at the intersection, it should be equidistant from all 3. And if it's equidistant from all 3, then you should be able to put a circle. So you can make a circle as long as they are not all in a perfectly straight line. Then it's not really a circle, is it? It's kind of just a big straight line. Infinite radius, you know? That kind of thing. Because then these lines diverge. But then they converge on the other side. Pretty cool. There's that. This one means nothing. I think actually it kind of does mean something. It's a parametric equation. And as you can see, it kind of shows you, what the hell is this? It shows you the rate of change. Now it's moving smoother because it's just taking a while to figure it all out, but it shows you the rate of change, I guess, at every single point. And it's just a little spiral I made using a bunch of equations. Okay. What's other stuff I have? Logarithm, spiral tangent. This one's a mess, I'm pretty sure. Yeah. Whoa. Oh yeah, I made a really cool pretzel with this one. Yeah, this one has a bunch of stuff you can change. It uses these things called like Lissajous curves, I don't even know. But it's basically like a parametric equation where you have something moving side to side, sine wave, or another wave going up and down. And you can change the frequency that they do that, and you get different shapes. What's I? So I think I is the wavelength? I actually have no idea what the hell I is. It's the size of the deviation thingamajiggy. This isn't perfect. I was just kind of going for a general shape thing, but that's kind of cool. There is this one. It's just a shape of constant width. I'm not going to show that. Here's when I was thinking about my guitar string, and I thought about all of the harmonics that should be playing on it, and then I accidentally ended up making a triangle wave. I didn't know it would do that. As you can see, it looks like it's actually, this is kind of how a wave would bounce in a string, I think. It kind of makes this, does bounce back and forth. And you can turn up N so that it looks more and more like a perfect triangle wave. Pretty crazy, weird looking stuff. I came upon this accidentally, and then I learned, because of that, I learned a lot about triangle waves and square waves, and how you can make them with a bunch of sine waves infinitely many. So I was starting to learn some pretty cool stuff. What's this one? Oh, this one's, I think this one's really simple. Oh yeah, this is how you can find the derivative of something in calculus. It's just a little visualization of it. I thought it would be nice. Basically, you just approach these 2 points together, and you get the perfect derivative at every point. That's how derivatives are found. That's it. You can move both points, can you? Okay, this is, yeah, I get it. Alright, there you go. Pretty cool stuff. There's that, the derivative. What was, fastest descent? I tried to make, yeah, Newton's method of fastest descent. It starts at N1. Where is N1? That's green. So it starts here, and then it draws a straight line down, and it tries to find the 0 by getting closer and closer to 0. And by the time we get to the purple one, it's actually pretty much perfectly at the 0. That's Newton's method of fastest descent. It's meant for finding the zeros of equations. What's another one? Squaring complex numbers. So I made this, as you can see, is if you think about these as complex numbers, each one of these is a complex number, and then all of these other 9 points are these complex numbers squared. So it makes this. I just wanted to see what would happen if you square a complex number, and this is what happens. So you get this little animation thing. I don't know what point corresponds to which. Oh, actually, I can kind of guess that this middle one corresponds to this middle one. So this orange dot is this red dot squared. Complex numbers, there's that one. I have all kinds of stuff. Let's see what I have. So much. I have a flower. This is a little bit just more artistic, you know. It's just a flower. You can change the amount of petals. I've made quite a few things like that. What else can you do? This used to be a more complicated. Actually, I think I have another more complicated one saved after it. No. Oh, this one's crazy. This one's pretty funny, I think. What was this one? Yeah. I was trying to visualize if you add together a bunch of sine and cos waves. I mean, sine and cosine waves are just like, they kind of mean like going around in a circle. So what this is it's the addition of a bunch of things going around in a circle. And if you just look at the y value, which is at the very tip of this orange thing, I don't know, this kind of moves, I think it's supposed to do in a square wave. Oh no, you look at the x value. Okay, I'm kind of confused here. But basically this thing curls. And it's running pretty slow. Wait, look at that. I forgot what the meaning of this was. It is running too slowly to really see it well, because I'm recording. Alright, here's another, I made a fractal-like equation because you can zoom in on it. And this is made by adding together many waves. They get progressively smaller in an exponential way, like this. That's the equation. I thought that was kind of cool. And you can do it at different degrees. So this is sine waves with increasingly higher. Well, you double basically each time, I'm pretty sure. Oh yeah, this time, each time it doubles the frequency of the sine wave and makes it twice as small, and then it adds it on. And then it just keeps on adding together those sine waves. It makes a pretty complicated, weird looking fractal. It's pretty great. And you can try with any number. Let's see, 5. That's going to be something. Pretty sure it makes it more, it's symmetrical if it's, the shape is obvious and symmetrical if it is an odd number. A is an odd number. And you can see that this is a fractal, and you can actually, yeah, pretty cool. Made more fractals after. Oh yeah, no, this one graph actually contains more than just that. Let's make that invisible. And let's look at a Taylor polynomial. What is this? Okay. So you can change the x, and it will approximate the sine function, or any function f of x, at that point by looking at the derivatives. The curvature, it looks at the curvature and makes a third degree. This is a fourth degree polynomial, okay? So it looks at the slope at the point, it looks at the value at the point, it looks at the curvature of the point, and it looks at the change in curvature of the point, and you're able to pretty closely match it at 1x. So this is a Taylor polynomial fraction thing. It ends. It's a fourth degree one. Pretty crazy. Cool stuff. I learned about that in a video, and then I thought I should graph it so that I could get it in my head. Here's another flower thing. Pretty cool. Petals. N. It's progressively finer and finer as N gets higher. And you can make these cool flower shapes. That's 1 petal, 2 petals, 3 petals, 4 petals, 5. Cool shit. I want to look at 1 petal. That's kind of funny. Weird. 2 petals. 3 petals is when it's really kind of flowery looking. Not really until you get to like there. I don't know. There's that one. Functionception. Oh, I like this one. This one's pretty good. How does this one's gonna take a little second for it to load, because it has integration in it, and integration of this function, which involves the derivative of another function. So I don't know. Okay, so what this does is, instead of, you could graph the exponential function on a perfectly straight x-axis line, but what if you tried to graph the exponential function on top of a sine wave, so that it's always perpendicular, sticking out perpendicular to the sine wave? And then what you get is that at the beginning, since the exponential function is close to 0, it pretty much matches up with the sine wave. Then as the exponential function goes crazy, since the slope of this line is wavering back and forth, the point where it plots the exponential thing does this. I mean, it's pretty cool. This is a little bit harder to visualize, but if you actually switch these two functions around so that it's 1.5 to the power of x, and then I do this one sine of x, let's say over 10, so that you can actually see it. It looks better without over 10. So essentially what this does is it puts one function onto another function. So you have your sine function, and you have your red exponential function, and it plots the sine one onto the other curve in a way that it keeps its wavelength, and it actually is a function of how far you've traveled along the wave. I used this parametric equation, and it's kind of cool. And I call it functionception because it's a function on top of a function. So there's that one. What do I have? Lagrangian polynomial interpolation. Wow, what a thing. What a word. This is a way of finding a function that goes through 4 different points. Lagrange. Is it Lagrange? I don't even know how to pronounce it, I'm not gonna lie, okay? I found this when I was looking, I looked up the words numerical analysis, and I read the Wikipedia page, and it showed you how to do this, and then I read the Wikipedia page on Lagrangian polynomial interpolation, and I read it until I finally understood the essence of what was going on, and then I made Desmos do it. So this is a third degree. You need a third degree function to go through any third degree polynomial to go through any 4 points. This is a way of interpolating somewhere. Well, Like, where do you think you would go if you were somewhere between these 2 points, given that you're a line? Yeah, anyway, you get the idea. What is the purpose? Interpolation. What's this? Fractal wave. See, this is the same idea as that other one. Where was it? This one right here. Remember where there was the sine? Anyway, this is the same idea. Except instead of using normal sine waves, I use square waves. So you can see it is a little bit simpler to look at. And it eventually stops because n is only 10. So it goes down. I think there's 1024. That's what the last frequency it adds on is. These are sine waves, and they alternate in sine, so that if they don't alternate in sine, see, they alternate in sine because I put a negative there, but if I take that away, then you actually just kind of get a staircase. And this is a staircase with, I think, like 1024 steps. It's 2 to the power of n, so in this case there's 4 steps. 1, 2, 3, 4, I guess. I don't know. That's that. Anyway, I think I prefer with the negative because then it makes a much more interesting thingamajiggy. Pretty cool. I like that one. This is one I thought of using. I used the Lagrangian polynomial interpolation thingamajig, and then I used it for, instead of a normal function, I used it for a parametric equation so that it goes through any point, any 5 points. So this is something that goes through any 5 points, and it plots a function on it. I made it so that the function, it looks like a spring, so the function actually shrinks when you compress it. But that's basically it. It goes through any 4 points that you would like it to. In a weird way, I'll admit. This is like not a super pretty shape, but it's just a way of doing it, okay? And it's actually, my computer's able to do this pretty quick, I think. I think it's pretty good, especially since it's just Desmos. Let's try and shrink that. It's whipping this way so hard that it's almost like it has like momentum to it, you know? Pretty cool thing here. You got that. And then, yeah, you can put any function on the curve. I just did that afterwards for fun. And then there is what the heck is trinomial? Oh yeah, I think this is called, I was watching a computer science video, computer file video, and they said bicubic interpolation, and they said that you could get any third degree polynomial, and what do you call it, get 2 points, and as long as you can know what the slope at those 2 points is, you can fill in the space in between. So I don't know what points it's using, so let's make, what were the values? S? Oh, F and I. So this is the initial. Let's just make it start at 0 for simplicity's sake. And end at 1. So what this does is it makes the slope at 0, -6, and the slope at 1, -9. So you can turn up the slope so that it's positive here. Let's make the slope, let's say exactly 1, so that this slope here is 1 now, and the slope here is still -6. So you can use any 2 slopes you like in combination. Let's use -1 and 1, and you get this shape. It just fills it in. It's another interpolation thing that just uses a trinomial. This is a way of graphing that a quick way that I figured out of graphing a 2D function in Desmos. It's pretty simple. You have an angle, you can look at it. It's pretty cool. And I have this k, which changes the function that you're looking at, actually, so that it looks like a ripple, and you can change the amplitude that you can see it at. So pretty sick. I like this one. I made another one for science. It's projectile motion, grade 11 problem. Not many equations needed to do it, but as you can see, it shows a little animation. It's pretty bad. I'm just going to stop that. But it shows you the path that a particle would take given a force of gravity. So we're making the force of gravity smaller right now, and bigger. And what is this? The angle. So you can change the angle that you shoot it at, and you can also change the velocity. So smaller velocity, changing the angle, bigger velocity. Shows you the path that it'll take. That's what that is. That's it. What's this one? Circle field. Nah, this one's not that good. Cool implicit. This is just a random cool implicit. I figured out that an implicit equation, they're kind of, when I first saw like one of those ones where it's like something of x and something of x is equal to something of y, and you use y and x, and it's just too confusing. But if you think about it as a 2D function of x and y on one side, and then just finding the intersection with the plane, it's kind of easier to visualize. Now, I don't know how helpful that was, but when I said that, but that's how I figured out something about this. So I was able to make this cool pattern. I wanted to make a repeated pattern that went out in all directions. I was able to do that with sine waves and shit. Here I wanted to figure out a way of putting any function onto any parametric equation. So in this case, our parametric equation is something as simple as a circle, but you can make it a figure 8, like a lemniscate, or you can make it any shape really, and it'll put g on it. This function. What was it? G. Yeah, the function g will be put onto the implicit. It would probably be better if I just showed you x of t and y of t by itself, so you can see how the blue traces it out. So let's just go x of t and y of t, and let's make it go to 2 pi. As you can see, it makes this lemniscate, and it's putting the blue function on it. It looks pretty ugly because the blue function's not that nice. But if I'm gonna change this to like z. Now there's no g of x. I'm gonna make another g of x that's simpler. Let's think of a nice simple, g of x, a nice simple function that we can put on. I think I'm just gonna do sine. That's pretty simple. And we have to make it a lot smaller so that and we have to make it a lot faster, like 20. And then that's pretty cool. So it puts let's get rid of z, and it puts the blue function onto any parametric curve. That's what this was for, a little math thingamajig. Horizon distance. This takes the radius of the Earth, and the x-axis is the height of a person in meters, and the y-axis is the distance to the horizon in kilometers. So if you are 2 meters tall, which you're probably not, but let's say you're 2 meters tall for simplicity's sake, your horizon, oh, that's 0.5. Okay, wait, no, I gotta go to x is equal. Oh yeah, and also you have to make the radius of the Earth correct. 6371, close enough. Okay, so if you're 2 meters tall, how do you get to x equals 2? X is 2, x is 2, x is 2. So if you're 2 meters tall, then your the y on this function tells you that the horizon is 5 kilometers away. So this is a function that tells you how far away the horizon is depending on your height and depending on the radius of your Earth. The smaller your Earth is, the closer the horizon is. So the smaller the y value is. So there's that. And then this is the last one that I have made just recently, actually, maybe within a few hours ago, 1 or 2 hours ago. And I figured out a while ago how to make a lemniscate using parametric equation. It was simple enough for me to imagine and think about how it just goes up and down and side to side with the sine function. So it makes this kind of lemniscate shape. So I figured, oh, let's try and make a lemniscate shape using implicit equations, since I have kind of unlocked a key way of visualizing and thinking of them for myself. So I was able to come up with this equation that also makes a lemniscate, and cool enough, I made this parametric one match up to what this one looks like. So they're actually completely identical, even though they look and work, these two equations work in two completely different ways. This one has an x and y that are a function of t, and this one has an x and a y, and it's like a big 2D function, and you're trying to find the zeros of that function, and when you find them, it's the same. I don't understand why this is. This is really cool. I don't know what the fuck that is. It's really awesome. And that's it. 25 minutes of just math. Alright, peace. And it's just like artistic stuff that or maybe not so artistic stuff that I would just like to do. Peace. Bye bye. Have yourself a good day. Have yourself a good day.